Welcome everyone to another OCP tab call. This is call number 144. Today we have Hasib, a PhD candidate at the university at New York University, specialized in network and systems. Hasib's research focuses on building scalable, low latency systems using general purpose networking infrastructure, an era that sits at the intersection of distributed systems, performance optimization, and time synchronization. In today's talk, he will present Onyx, a system designed to bring financial exchange to public cloud, a major challenge given the cloud's best effort nature and the ultra low latency, fairness, sensitive requirement of trading environments. So Onyx employs an overlay multicast 3 to disseminate market data to over 1,000 participants with less than 1 microsecond difference in time perception, in data reception time, ensuring fairness across participants. It also introduces novel techniques to mitigate latency, variance, and new scheduling policies at the improves exchange throughput and stability under bursty networks. Please join me welcoming Hasib. And Hasib, the floor is yours.
Nice. Thanks, Ahmed. Okay, I'm Hasib. I'm going to present my paper, Network Support for Scalable and High Performance Cloud Exchanges. This work was done with an amazing team, and although I'm just the only one presenting here. So I'll start right away with a primer on financial exchanges. So there is typically an exchange server, and there are going to be several market participant servers. The exchange server will have some market data to disseminate to the participants. And there can be several such market data points, which goes from the exchange to the participants. And then the participants may also have some trade orders, which goes from the participants to the exchange on the reverse side. And then the exchange server also maintains a record of all the orders received from the participants, and there are several mechanisms to keep such a record. One very famous way is to have a limit order book, where all the bids and asks received from the traders, they are put into a book, and then there is some algorithm for matching the orders with each other. So for example, if there is a bid which can be matched with an ask, these orders will get executed. And if there are bids and asks which cannot be matched with each other, they just stay in the book. And there are also some algorithms which are called matching algorithms, which decide how and which orders should be matched with each other. One very famous algorithm is price time priority, where all the incoming orders, they are sorted into their respective price levels. For example, we can see in this snapshot of a book, there is a price level 1, 2, 3, 4, and so on. So the incoming orders, they go into their respective price level, and then each price level is sorted based on when the order was generated. To maintain fairness, when some price level is selected for execution, we typically select the oldest order from that price level. And this book also has, as we can see, there are bids and asks, and there's a separation point between them, which is typically called mid price, and it reflects the true price of an asset. So if there is a bid which crosses this mid price, it may get matched, and vice versa for asks. Now, orders which are closer to the mid price, whose price is closer to the mid price, they will immediately be matched. They have a higher chances of immediately getting matched. For example, if a bid arrives which is $4 or $5, it has way higher chances of getting matched compared to a bid which arrives for price $1. And orders away from the mid price, they will potentially be matched in the future when the mid price moves closer to them. So for example, if all the bids at the price level 2, 3, 4 are exhausted, then the bids from the price level 1 will be chosen for execution. So the positions in these price levels, it matters. If the position in this queue is high, then higher chances of getting matched, and this creates a competition among market participants. So participants wanna be, if they choose a price level to hold a position in, they would wanna be ahead in the queue in that price level, so that if an opportunity for order matching arrives, they are the first one to get matched. So they want to put orders as soon as possible. Speed matters a lot in this scenario. Now, traditional exchanges, they are built in private data centers or co-location facilities where the exchange server and the participants, they are co-located and they are connected with equal length wires. Why equal length wires? For example, if some trader issues an order before the other trader, we would also want the server to see the earlier generated order before the second one. So this network asynchrony is, they try to remove it as much as possible by employing equal length cables and low jitter switches. These people are so much crazy about speed that some of the traders, they when they see a packet market data coming in on the wire, they start generating a trade order and they start sending that packet. And once they receive the market data packet in full, they may decide, oh, they didn't wanna put an order, so they scramble the checksum of the outgoing trade order packet. So they don't want to waste time in waiting to receive the entire packet and then putting an order. So that gives an idea how much speed is a concern in these settings. Now, can we use the public cloud to build and scale such financial exchanges, which are typically built in private data centers with specialized infrastructure? Can we do it on cloud, which is very much a general purpose networking infrastructure? What are the benefits of doing that? It reduces constraints of physical space around the exchange server. In the co-location facilities, there is an exchange server, and all the participants, they are located nearby with equal length wires, which also introduces constraints of physical space. If we can build exchanges in the cloud, we will not run into such space issues. And it can allow us to have a huge scale. Thousands of traders can be supported, while the typical number of traders which are supported in on-prem exchanges is 100 or 200 or so. And it lowers the barrier to entry for launching new global markets, as launching a new exchange is just getting some VMs up and employing some overlay networking on top of it to get exchange running. And it also allows access to various analytics and ML services which reside nearby in the cloud. And then there are many typical benefits of cloud, for example, offloading management of infrastructure, reduced cost, and etc. But there are also going to be trade-offs when we build an exchange on the cloud. The latencies will be higher, and the fairness guarantees, we might have to coarsen them a little. So we'll take a deep dive on that. Before that, this is a graph which shows latency between a pair of VM in the public cloud. We can see that there's a high latency and latency variance. Sometime, most of the time, the latency is between 50 and 100 microseconds, but it jumps to 150 a lot, and sometimes it even crosses 300 microseconds. So latency varies temporally. Over time, the latency may change, and latency also varies spatially. So if we have two pairs of VMs, whatever is the latency between one pair, it may differ from the latency between the second pair. Now, this is important because we want the latency from the exchange to all the traders to be same, but the VMs in the public cloud do not exhibit that. This is unfit for fair competition, and that's where Onyx comes into the picture, where we employ mechanisms, where we develop mechanisms to achieve fairness and high performance at scale. So now I'm gonna present where Onyx stands in the, like, compared to the other exchange mechanisms. So we have four axes here: economy, fairness, performance, and scale. Away from the center means better. So on-prem exchanges, they do bad on economy and scale. They are very expensive because the specialized infrastructure is used and there are high fees for those equal length and low jitter switches. and the scale is low, only 100 or 200 MPs in a typical exchange, while the performance is really good. The latency difference between participants can be very low. It can be as low as the data reception time difference can be in the order of nanoseconds. The fairness is very good, and the performance is very high. The latencies on the links are it can be single digit microseconds or sometimes even lower. And then there is another spectrum, which is web APIs, doing trading using the web APIs. For example, exchanges provide market data feeds on the web APIs. You can use those, consume market data, and take a decision to do some trade or not. Now, it's very cheap. There's like almost no fee for using such web APIs, and the scale is huge. A lot of the thousands of market participants typically use this web APIs, but the performance is bad. The latencies are going to be way higher, and the fairness guarantees are almost negligible, because it's really equivalent to the latencies experienced in the internet. If you're residing closer to an exchange, you may have a low latency, and if you're away in a different continent, you may have higher latency. And then Onyx, this is at the center where we try to do good on all four axes, where we try to improve performance as well as fairness while achieving a low cost and high scale. Okay, so now that we know where Onyx stands in the other works, let's quickly see what Onyx, this paper, is about. First, it has a multicast service that disseminates market data to 1,000 participants, each receiving a message within 1 microsecond of each other. That's required for fairness. And then we have have a order submission service, which effectively handles bursty traffic while maintaining fairness of competition among the participants. And we prototype it on AWS and GCP. We'll go into details of each of these things. So this is the agenda for rest of my presentation. We'll talk about the definitions of fairness and how we relax them, and it includes scalable outbound fairness and scalable inbound fairness. In the scalable inbound fairness, we'll discuss a scheduling policy that gracefully handles bursts. So let's start. So fairness, there is two kinds of fairness: outbound fairness and inbound fairness. In outbound fairness, we have an exchange server. It sends market data to all the market participants, and market participants may receive this data, this message at different times. Let's say T1, T2, and T3. This difference in data reception time for any two participants should be zero. That's outbound fairness. That means all of them receive the data simultaneously. And in the inbound fairness, we have market participants generating trade orders, which go to the exchange server, and orders should be seen by the exchange in the order of their generation. So almost there should be no network asynchrony, network reordering, or anything. Now, these are the two ideal definitions of outbound and inbound fairness, but it's very hard to achieve these. We have what we can achieve in practice and what other systems achieve as well. Is this the in the outbound fairness, we try to reduce the difference between data reception time across participants to be almost equal to zero. In this work, we try to achieve less than 1 microsecond, while the on-prem exchanges can achieve less than couples or tens of nanoseconds. And in the inbound fairness, orders should be seen by the exchange server in the timestamped generation order. Whatever, because there is some difference between an occurring of an event and attaching a timestamp to it. This difference, this distance between the application and the clock, this can vary across different traders. So we do not handle that. We just say that once a message has gotten a timestamp, will ensure that exchanges sees these events in the order of their timestamps. And achieving fairness while being performant at scale, like having 1,000 participant VMs, that's our goal. Okay, so we'll start with the first, which is the scalable outbound fairness. The outbound fairness, it's achieved by a very simple primitive, which we call hold and release, which is not very scalable. We'll see how we make it scalable, but first let's see what is hold and release primitive. So there is a sender and there are several receivers. Thus, we synchronize all their clocks with each other, and then the sender, it whatever message it will send to the receivers, it attaches a deadline to the messages, and then this message is multicasted to all the receivers. The receivers may receive this message at unpredictable times based on whatever is the latency between the sender and any of the receiver. But all these receivers, they will process the message at or after the deadline. So ideally at the deadline. So the deadline is set sufficiently in the future that all the receivers have received the message. And if they have received the message before the deadline, they'll hold it before processing and they only process it at the deadline. Now, there are some questions about trust. We can get to those later if we have time. But for now, let's assume that receivers cannot really violate this hold and release mechanism. So if the deadlines are set sufficiently in the future, we end up achieving this simultaneous delivery, like the data reception time, the data processing time can be very close to zero. So this primitive does not scale, and there is a tension between latency and fairness. If I set the deadline to be sufficiently in the future, I'm sure to achieve fairness that everybody would have received the message by that time, but it may increase the latency a lot. But if I try to reduce the latency and try to set tight deadlines, then any latency variation, any latency spike, which are very common in the public cloud, they may lead to violating fairness. We scale this mechanism by proposing an efficient market data multicast mechanism, uh, which starts with a very simple idea. Let's use a multicast tree. A tree of proxy nodes is utilized that helps scale the multicast. So if this is an exchange, instead of this exchange sending messages to all the receivers, it only sends messages to a few proxies, which in turn do the same until the messages reach at the leaves, which are the receivers. Now, the benefit of this is shown in this graph. So direct unicast would be exchange sending message to all the receivers one after the other. And the tree is using this proxy mechanism. And the x-axis on this graph shows all the receivers, the receiver IDs, and the y-axis is the one-way delay from the exchange to the receivers. In the direct unicast, the latency of the later receivers, it's higher than the earlier receivers, while in the tree that the latency is much more balanced. So instead of so earlier the latency to one receiver could be way higher than the latency to other receiver, which also makes defining deadlines harder. But now we have much more balanced latency, which leads to having better deadlines. Now, although we have this balanced latency, but we have way more nodes in the path of messages. Each of this node is a VM. Um, and more of these nodes in the path of messages means more room for performance variation. And a VM's performance may change. The links between VMs, they may show some straggler behavior. So there are many rooms for performance variation, which increases latency variations. So we deploy mechanisms to handle with that. So for latency spikes on the links, we have this mechanism called round robin packet spraying, where the parent child relationships in the tree, they continuously keep on changing. So no link is used for consecutive messages. And the proxy node, for handling proxy nodes performance variation, we have each node have multiple parents so that at least one of the parent is not going through the performance variation and the message may arrive on time. And then the receiver VM's performance variation, where we say that each trader will have two receiver VMs, each of the VM running the same trading algorithm, which is a deterministic state machine, which has the same input and leads to that identical output. Now, I will not go into details of each of these techniques, but these techniques help us remove various sources of performance variations in the tree. and we end up having a multicast mechanism where the latency from the exchange to all of the traders is very much the same. And on top of that, when hold and release is applied, we can easily achieve simultaneous delivery without inflating latency too much. So now I'll jump to the second part of the talk where we have inbound fairness and how we achieve a scalable inbound fairness. There are two main components to it: a sequencer, which helps achieve inbound fairness, and a scheduling policy, which helps um, tolerate bursts of orders from the traders so that the performance of the exchange can be high. So in the sequencer, we have an exchange server. We have several market participants. The sequencer sits at the ingress of the exchange server. It can be a process in the exchange server where all the incoming messages are fed into that process, and the output of the process goes into the limit order book or whatever the algorithm is running for matching. Now, the sequencer guarantees that orders are seen by the exchange in non-decreasing order of their generation timestamps, and it assumes clock synchronization between participants and the exchange server. There is a strawman solution to achieving this guarantee, which is whenever a message is received, we wait a fixed amount of time before further processing it. The exchange waits a fixed amount of time before further processing it, so that if there are messages which were generated earlier than this message, but they got reordered in the network, they have enough time to arrive. This also works well enough with a small number of receivers, but as the number of receivers increase, there's more room for performance variation. There's more room for network reordering, and defining that threshold delay becomes hard. What we end up doing, and it also has this latency and fairness tension. If you wait a lot, you are almost guaranteed to receive the messages which were generated earlier, but the latency will be higher, and then vice versa. What we end up doing is that we can use the knowledge of a fixed number of market participants, that in this application we know how many market participants are there. So we can just try to wait for one message from each of the participants and then sort it based on the timestamps. So clients, they attach message generation timestamps to all the outgoing trade orders, and the sequencer waits for at least one message from each client, and it releases the one with the smallest timestamp, and then it waits again. So by doing this, iteratively, we end up achieving that guarantee that exchange will see the messages in the non-decreasing order of generation timestamps. There is a drawback here that liveness may halt under client failures. If some client does not generate a trade order, that may hold up the entire sequencer for releasing any message. We have a solution in the paper where the clients are supposed to, if they are not generating trade orders, they are supposed to generate heartbeats. So that helps us know that whether some client is active and whether they have any message. If we have received a heartbeat with timestamp T, then we know that if there was any trade order with timestamp smaller than T, we must have received it because we use TCP channel, which provides in-order delivery. The safety is guaranteed if clocks are perfectly synchronized. In practice, clocks are not perfectly synchronized, but we ensure that the clock synchronization accuracy is sufficiently high compared to the time granularity of interest. So we only deal with timestamps in this application at the order of microseconds, while the clock synchronization is in the order of nanoseconds. The clock synchronization errors are in the order of nanoseconds. Now, we have this simple sequencer which achieves inbound fairness, but we end up with this performance problem, which is in-cast congestion. As the numbers of traders increase, the in-cast congestion at the exchange occurs. We see the opportunity to reuse the multicast tree in the reverse direction to reduce burstiness behavior at the ingress of the exchange. Um, Clients get partitioned into groups where each proxy node handles a group of messages. So the fan-in factor of each node decreases. Instead of the exchange receiving messages from all 1000 participants, it may receive messages only from the proxy nodes, which may be 10. And then each proxy node is doing so. So reduced fan-in leads to lower packet drops because of lower in-cast congestion. And it also moves the queues from the exchange's ingress to the tree nodes. Somewhere, some packet queue has to form because of this in-cast congestion. Without reusing the tree in the reverse direction, the queue is forming at the ingress of the exchange, which is not under our control as a cloud tenant. It is not under my control. It overflows and the packets get dropped and the retransmissions happen. But if we are using a tree, all these nodes, all these queues, they form in the proxy nodes, which are under my control, and I can do some fancy scheduling on them to improve the performance of the exchange. So there we have a limit order queue. This is a scheduling policy which helps tolerate burst of orders from a large number of traders. During bursty market activity, the exchange server may be overwhelmed. And there we have a LOQ, a limit order queue, a domain specific scheduling policy. It schedules orders in a way to avoid idling the matching engine. Matching engine, it's in the exchange server, and this is the one which decides which orders should be matched with what other orders. And it uses the knowledge that the orders are matched by some specific priority algorithm. So it tries to implement that algorithm all over the tree in a way that we only send orders to the exchange which immediately needs to be matched without violating any kind of fairness. So if this is the limit order book, if this is a state of the exchange at any point in time, and these orders arrive, $1, $4, 5, and 2, let's say these are all bids, then we know that 1 and 2, they are far away from the mid price. And 4 and 5, they are very close to the mid price. So if these bids were queued up at any proxy, we know which ones to prioritize and which ones to deprioritize. But if we naively do it, it will violate inbound fairness, because it's possible that although we think 5 is the mid price, but by the time these orders, if they were to be sent to the exchange, and the exchange processes them in the order of their generation timestamps, the mid price would have moved and 1 and 2 should have been prioritized. So naively doing this is a bad idea. It will not maintain inbound fairness. So how can we do such a scheduling, such a reordering of queued up orders at the proxies, which also uh, preserves inbound fairness. So for that, I'll set up the picture how where is the opportunity for such scheduling. So if this is the exchange server and these are the market participants, and the market participants send orders to the exchange, and we have a FIFO fabric, we are not using any kind of scheduling. It's just a first in, first out fabric. Then all the orders which go through it, they will appear at the ingress of the exchange. And let's call this sequence IFIFO. And then they go through the exchange, they go through the matching engine, and they are executed, and whatever is the order of the output, let's call it SFIFO, the sequence FIFO. And then we have a similar setup, but instead of a FIFO fabric, we have a LOQ fabric, this special scheduling policy that I developed. And the orders go through this fabric and they appear at the ingress of the exchange in some sequence, let's call it ILOQ. And then they go through the exchange and they get executed in some certain order, and then we get this SLOQ. Now, for maintaining fairness, we need to ensure that SFIFO equals SLOQ. If they are not equal, that means LOQ is not preserving fairness. But IFIFO does not need to be equal to ILOQ, and that's where the room for any kind of packet reordering or scheduling comes in. So S3 being equal to SLOQ, it preserves fairness, and this does not need to be equal. That's the room for improving performance with some kind of packet reordering, with some kind of scheduling. Now, we have the knowledge of the matching engine, and we have this constraint that S3 needs to be equal to SLOQ. We can figure out some way of reordering packets, like which packets should be reordered, so that when they go through the matching algorithm, the SLOQ is still equal to S3. That's where the room for developing any scheduling policy is. Now, I will not go into details of what this LOQ policy is, but this sets the stage. How can such a policy be developed which preserves fairness? We are also working on a follow-up of this work where we encode these constraints of preserving fairness, and then we have any exchange matching algorithm. Right now, we're using price time priority matching algorithm, but there can be any other algorithm, and automatically such a scheduling policy is synthesized so that when the sequence of orders goes through that matching algorithm, the SLOQ is still equal to S3, but whatever reordering, packet reordering room we can get from the scheduling policy, that may improve performance. So key idea here is still the same, that we will separate critical and non-critical orders using mid price. Like we'll see whether this order has higher chances of getting matched, this order has lower chances of getting matched, but we'll only prioritize a critical order over a non-critical as long as SLOQ will stay the same as SFIFO. Okay, so I'll quickly jump onto the evaluations, and let me just take a look at the time as well. Okay. So first I'll show the performance of multicast surveys. We have this graph, we are going to show the CDF of multicast latency. Overall multicast latency means the max whenever some messages are multicasted from the exchange to the participants, what's the max latency experienced by any of the receivers. And we compare it against AWS Transit Gateway based multicast, direct unicast. Direct unicast is simply exchange sending messages one by one to all the receivers, and this system Onyx. So AWS Transit Gateway based multicast, it's provided by AWS, but it's not really switch multicast. It's also overlay multicast, where the sender just sends the message to a transit gateway, and the transit gateway tries to efficiently replicates it and sends to all the receivers. You can configure all the GMP groups in this transit gateway. We end up doing better than both AWS Transit Gateway and Direct Unicast approach. But what's more important here is that Onyx, the CDF is very steep. All the higher percentiles are very much similar to the lower percentiles, which shows that we remove a lot of performance and latency variations. And then let's talk about delivery fairness of multicast. We measure it by delivery window size, which is when a message is multicasted from the exchange to all the receivers, what's the time difference between the earliest reception time by any receiver and the latest reception time by any receiver. The difference between those earliest and latest reception times, we call it delivery window size. Like all of the receivers received a particular multicast message in that window. And we have Onyx and we have a prior system CloudX. Onyx is we compare it under different configurations, and we see that we are able to achieve the delivery window size of close to zero. Close to zero here really means less than 1 microsecond. And it's the same as the other system CloudX, but the CloudX does not scale well. It does not work for more than 100 receivers, but Onyx works and gives the same performance with 1000 receivers. And this is the multicast latency as we go from 100 receivers to 1000 receivers. At 1000 receivers, we do see a long tail. And then this shows that how LOQ is able to gracefully handle bursts of orders. So for this, we have there's an experiment timeline on x-axis, and y-axis is the packets processed by the exchange per second. And we are comparing Onyx, this system, with a prior system, CloudX, and the the shaded areas represent bursts of orders. So the cumulative order generation rate by 10 market participants in this experiment is 100,000 packets per second. But during burst periods, during shaded regions, the order generation increases by 20x. CloudX, it does not use knowledge of, it does not use any domain knowledge to prioritize some orders over the others to improve performance. So it is not able to keep up with the load, and it is even processing packets when the load generation stops. Load generation stops at 20 seconds, but CloudX ends up building huge queues, which needs to be processed even after the load stops. But Onyx is able to smartly process some orders which need to be processed right away, while um, deprioritizing others which can be processed later on without affecting any fairness. So Onyx ends up achieving higher throughput. And here I just show if we have the entire setup same, like we are using the tree, a multicast tree in the reverse direction, but we just replace the limit order queues scheduling policy with a FIFO. So what's the result? And we see that, and that's shown here, that limit order queue as the burst arrives, its performance improves, and as the burst goes down, it has processed all the queues, and so that its performance, its order matching rate also comes down. While FIFO cannot do that, so it ends up building queues, and those queues are serviced as the experiment progresses. Now, this is the order matching rate. I think I don't have the latency graph here, but what ends up happening is that the latency of orders with LOQ remains very low because it's able to process them as they are generated. But FIFO ends up building queues, so the latency of orders is way higher in case of FIFO. So concluding remarks, cloud financial exchanges can be realized by developing new primitives without specialized infrastructure, and clock synchronization is very helpful in developing such new primitives. Some performance and fairness guarantees need to be accordingly relaxed. Such exchanges present a new operating point in the cost performance curve, as we discussed, and application specific scheduling policies can have a significant beneficial impact while preserving fairness. And as we discussed, where is the room for doing scheduling if we have to preserve fairness? There's a detailed paper that appeared in SIGCOMM 2025. Please have a read, and thanks. Let's have a Q&A session.
Wonderful, thank you. So let's have those open the floor for questions.
How does it scale beyond 1,000?
Why it does not scale beyond 1,000?
Or no, how does it scale? Does it, I mean, would it work if I had, say, 10,000 or 100,000 or 1,000,000? Or
So the techniques themselves, they do not really say that it has to only be scaled to 1,000. It can scale to more. We have tried with 1,200 and 1,500. But we didn't go an order of magnitude higher than 1,000. For example, we didn't test 10,000. Maybe there are new performance bottlenecks at 10,000. So the techniques may need to be changed. So we have not explored that. And the reason for that is basically the resources, because 1,000 market participants mean 1,000 VMs in the cloud that we rent to perform this experiment. We did not
see.
10,000. So it's up to, it's up to exploration if these techniques are used but scaled to 10,000, whether they still give the same performance or something more needs to be done.
Thank you.
I have a question, Hasib. How how can you apply this, let's say, to gamers? I mean, it's kind of similar, right? Like you have some race condition, you have like a zero sum situation, and you have to pick like one winner. So let's say if you have, because I mean, Oleg and I, we worked on some technology. I mean, it's still like in the infancy, like to bring timing to the end node, to the end users. Would this benefit from that? Just wondering.
Let me think. So I will just say that we did explore one angle, which was cloud gaming, where some event happens in a game and it needs to be broadcasted to all the gamers, and all of them should see it at the same time that some event happens, because they can generate a reaction to that event. And there we saw this kind of multicast, this deadline-based messaging may help. But we have not really like prototyped or anything. But there is a room for using this deadline ordered multicast, we call it, using this deadline ordered multicast in cloud gaming.
One more thing, like, is it fair to say, like, in this system, you delay everyone to the slowest to create fairness? Is it fair to say something like that or not?
That's a very accurate statement.
Okay.
And it's actually a characteristic of all such systems, where to achieve fairness, you slow down everyone to the slowest player.
Makes sense.
Yeah, and that's why we try to, for the multicast tree helps us balance the latency, so that first we reduce the difference between the fastest and the slowest. We make them balance, and then we make everyone slow so that they match the slowest receiver. Yeah.
Thank you. Any more questions?
I have a question. So you talked about matching the slowest receiver. Is there a certain time scale that you require? In other words, you expect all the clocks to be synchronized to, a nanosecond, a microsecond, a millisecond. What is the requirement that everybody should be synchronized to?
Right. So the time granularity of interest for the application is microseconds, that when we talk about data reception time difference, we'll say it's 1 microsecond or higher. Will not go smaller than 1 microsecond. That For that time granularity, the clock sync errors need to be negligible compared to 1 microsecond. So we have the clock sync errors in the order of nanoseconds.
I
So
see.
yeah, when the clock.
No, in AWS, when you ran this, was it all in one data center or were they geo-dispersed data centers?
They were only in one data center, and we Huygens
That's nice.
algorithm for clock synchronization. We don't use AWS is on, because they cannot achieve that clock synchronization that we require.
Yeah, that was good information. I'm just curious on if you'd want geo-dispersed, cloud exchange, right? Because you might have people in, say, Chicago or New York or Los Angeles or Miami, all trying to trade at the same time,
Right.
or internationally, even Europe, Asia.
Yes.
So, but in that case, the time synchronization would have to be in the microseconds or nanoseconds, which I
Right.
don't think they're at quite yet.
Yeah.
Okay.
So right now, even for a single data center, we require the time synchronization to be in nanoseconds, so that our guarantees can hold at microseconds. And if we were to have it geo-distributed, then either we increase the time granularity of interest for the application, because the errors are going to increase from nanoseconds to microseconds at least. Like they're going to be milliseconds if we go with off-the-shelf clock synchronization algorithms. But let's say we can achieve microsecond level granularity across data centers. That means the time granularity of interest for the application needs to be at least an order of magnitude higher than whatever errors we are seeing, so that we can ignore the errors. That would mean that saying all the receivers receive data within 1 microsecond of each other, this guarantee might not be possible. It might have to be 100 microsecond of each other or a millisecond of each other. So the guarantee may need to be cautioned accordingly.
Yeah,
Makes sense.
yeah.
Have you talked to any like exchanges like Bourse or NASDAQ or NYSE or anything like that to see if they were interested in this kind of technology?
We are in talks with some, mostly not the exchanges, but the trading firms, which are interested in the techniques to load the latency variance. We haven't talked to an exchange yet, but yeah, we are trying to do that as well.
Thank you.
One more thing that Hasib, I think, can become I don't know, an issue or challenge or whatever you name it, is the presence of, let's say, bad players, technical bad players,
Right.
that they can claim they are getting like the time delayed or something, but take advantage of it.
Right.
So have you thought how that can be? I mean, it's really a far stretch, but I'm just wondering, did you have
So
a
yeah, that's actually a really good question, because the traders do have an incentive to lie. They have an incentive to lie about the latency they are experiencing. They have an incentive to lie about the timestamp they attach to the messages. So what's the trust model? That's the question. We have some debate in the paper, but I would say what's most practical solution to this is the receiver VMs as well as the exchange VMs. They need to be under the control of the exchange, and then exchange just loads the trading program of a trader onto the receiver VM, while rest of the VM is still under its control. The program, hold and release program, the timestamping program is under the control of the exchange, and just the trading program is taken from the trader and loaded into the receiver VM. Now this deployment model is the best when it comes to performance, but there is a trade-off that the trader has to reveal its trading program to the exchange. The solution to that is the exchanges are actually required by law, in at least in US, to not reveal that information to anybody else. But we also explored some AWS Nitro Enclave solutions where a TEE is created. One VM can have a parent VM where the exchange is programmed for timestamping all the programs that we don't want to be violated run. And then we have a trusted execution environment where the trader's program is loaded onto it without the exchange knowing what the program is. So there are such deployment models that needs to be discussed. But as I said, the simplest model is the exchange controls all the VMs and just the trading program is loaded into the receiver VMs. That works well. That gives us security guarantees as well as the performance.
Just thinking loud, would something, let's say, like blockchain help? Let's say, for example, you have different nodes, because I mean, yeah, putting in centralized is perhaps a solution, but I mean that's like such a attractive thing for hackers to figure out how to inject whatever it's going on there. And like, I mean, it's really, I don't see it very difficult. Like you can have, let's say, two machines sitting side by side, one of them with extra latency, physical latency, like you just
Right.
put like, I don't know, extra 200 kilometers of fiber around it.
Yeah.
And then while they can also talk to each other, one of them is getting the benefit of, oh, I'm far. and then the other one is like, I'm right there, and then they figure things out. So what I was thinking is, if you have the local clock being able to constantly randomly check with other clocks, basically the what do you call it, the gossip algorithm, like they basically send to each other messages randomly to other machines, and they get judged by that to if the messages are from the future. And either way, like basically if someone is thinks everyone is from the future, well, they are wrong, like, or something like that, like if someone doesn't like disagrees with everyone, well, they are wrong. But if someone is agreeing with most and there's one that is like, disagreeing with, like, you can take them out. So that shows me it's like somehow like it's like a blockchain thing, where you look for majority and you make it disaggregated. But again, I don't know that this is a good research question for you. I should talk to your advisor, bring it in your defense.
Yeah, for sure. Yeah. So I think it's an interesting point to think about. What you're saying is we run some protocol between these VMs to figure out which VM is lying about its timestamps.
Exactly.
But okay, that protocol, the VMs themselves are running that protocol. So okay, I mean, on top of my head, it's gonna be very hard to
You're
deploy
right.
an
You're right.
algorithm.
Again, it's a game theory thing. You're
Yeah.
right. That can be spoofed as well.
Yeah. So that's why, I mean, yeah, like for this paper, we just said we will not let the traders control the VMs.
Yeah.
But yeah, as a follow-up, there could be something, hey, what if traders want to control their VMs? How we can figure out whether someone is lying or not. Now, there is some work, it reminds me of Pompeii, that way, I guess it was in SOSP a few years back, where they have a consensus mechanism and they try to see whether some Byzantine nodes they can dictate the order of the ledger. So if some ledger is being consensus upon, can some bad nodes try to say, okay, this index should hold this message and this index should hold this message, and they develop some game theoretic. It's very much social theory based solution. How small number of nodes should not be able to dictate the order of the overall messages. I can see something like that being applied here, but the results from that paper themselves were, in theory, you cannot, but they develop some mechanism in what cases it can be done and in what cases it cannot be done. So applying that here could give us some interesting results. Maybe not practical, but it will at least tell us what can and cannot be achieved. Yeah.
Yeah.
It's definitely game theory and social theory type of problem.
Yeah, it's so many like different aspects, like
Yeah.
all of them show up in this.
Yeah,
Great.
definitely.
Did we have David here? I don't think
No, I didn't see him here.
I wish we had David.
Yeah, he shouldn't be here.
Metal zero, they don't count because metal zero is confirmed.
Yeah.
Yeah,
All right.
metal zero is
Any more
confirmed.
questions from the audience?
So from metal one to here is how many?
Okay. Hearing none, again, well, thank you again, Hasib. Looking forward to having follow-ups perhaps from this, this is definitely something this audience is very interested in, because this touches the aspect of what can we do with this, because I mean, you brought up a lot of these, let's say, applications that can use perhaps if bring precise time to, to the end node. Let alone like, data centers and all of these things. And it's great, like to have like trusted users at the end nodes with a trusted time. And as you showed, like so many things can be used to create fairness. So you don't have everyone crammed, let's say, by like data centers to just go with latency or something. But I mean, it comes with its own challenges as well. Yeah, so thank you again for the informative presentation, and we look forward working with you. And we'll have in 2 weeks, I think it's a presentation regarding, RTK technology by Yudan Yi. All right. We'll see you in 2 weeks.
This is like 19 metal.
And thanks
Thank
for
you.
inviting me.
You're welcome.
Thank you very much.
Bye, everyone.